Hello, everyone. I'm Keke Ying from Beijing Institute of Technology. Today, I'd like to share our team's recent work with you. The topic of this presentation is Reconfigurable Massive MIMO, harnessing the power of the electromagnetic domain for enhanced information transfer. The corresponding article of this pre has been uploaded to arXiv, and more information about our group can be found on our homepage. The talk today includes 6 parts: Introduction, EM radiation gain of reconfigurable massive MIMO systems, system model of MIMO, 3-level pre-coding for MIMO, performance comparison, challenges and future directions. Recalling the development of MIMO systems, the exploration of the spatial domain degrees of freedom has been the focus of communication systems since 4G. Early small-scale MIMO systems used the transmit or receive diversity to combat the adverse channel circumstance. Furthermore, spatial multiplexing was then introduced to improve the number of simultaneously transmitted streams. When massive MIMO was introduced in 5G, the base station with tens of hundreds of antennas is able to provide directional beams toward target users, which improve the quality of service significantly. More recently, the extension to extra-large-scale MIMO has motivated researchers to utilize the near-field properties for enhanced transmission or other applications such as localization. From the evolution of the MIMO systems, one can see that expanding the array aperture is one development tendency to further improve the throughput of MIMO systems. However, there are also some emerging obstacles when putting massive MIMO, or XL MIMO, into practice. First, the hardware cost and the power consumption of massive MIMO increase severely with the increased number of antenna ports, which make large-scale fully digital arrays highly expensive. Second, the most common way to deploy an antenna array is to mount it on the pole, which means that the aperture of an antenna array cannot be increased without limit due to the windage resistance constraint. Several efforts have been put into the evolution of MIMO systems. First, the hybrid MIMO architecture has been introduced, where a phase shift network is utilized in the fully connected array, which divides the original high-dimensional digital domain processing into a high-dimensional analog domain operation and a low-dimensional digital domain processing. Therefore, the number of RF chains can be significantly reduced. To further reduce the number of phase shifters, the subconnected array has been proposed. From fully digital array, fully connected array to subconnected array, the hardware design becomes easier to implement at the cost of reduced degrees of freedom for the associated signal processing. Although various sophisticated pre-coding algorithms have been proposed to compensate for this performance degradation, how to achieve a satisfactory trade-off between hardware cost and achievable performance remains an open problem. Another method is to excavate the unexplored DOF within the limited aperture size. As a theoretical concept, holographic MIMO aspires to provide maximum DOF for the manipulation of the EM field. In contrast to conventional MIMO systems employing half-wavelength critical antenna spacing, holographic MIMO systems are assumed to have a continuous aperture surface with infinitesimal antenna spacing. Each point on the surface has theoretically independent adjustability of the corresponding excitation current. As a result, holographic MIMO is expected to have the capability to flexibly generate any current density distribution on this aperture surface. Therefore, holographic MIMO should be able to customize any desired EM properties, for example, polarization, radiation pattern, etc. However, it could be practically challenging to engineer such idealized MIMO systems since the mutual coupling effect becomes more severe as the antenna spacing decreases, and the antenna efficiency decreases with the reduction of the antenna spacing. Therefore, there is an urgent need for one solution that can break the performance limits of aperture-restricted MIMO at a low hardware cost. Before we move to the proposed architecture, we would like to give a short review of reconfigurable antennas, which is also the basis of our proposed reconfigurable MIMO system. The concept of reconfigurable antenna dates back to the electronically steerable parasitic radiator, ISPAR, antenna proposed in the 1980s. As shown in Figure 4, the prototype of the ISPAR antenna consists of one active element and multiple parasitic elements. The parasitic element is connected to different reactive loads. By changing the value of the loads, the current distribution of the antenna is changed, which thereby changes the radiation pattern of this antenna. In the original ISPAR antenna, the direction of the radiation pattern can be changed by properly tuning the on-off states of certain circuit elements, such as varactors and pin diodes. With the development of hardware fabrication methodologies, the advanced reconfigurable design can change the operation mode of a single antenna in a compact antenna structure. More recently, researchers proposed a reconfigurable compliant mechanism antenna, which exhibits continuously tunable ability across a broad band of frequencies. Another fascinating structure is the reconfigurable pixel antenna. As shown in Figure 6, the reconfigurable pixel antenna consists of a patch layer and a parasitic layer. The patch layer carries the patch antenna, which couples the energy from the RF chain into space. The parasitic layer is composed of multiple interconnected metallic pixels. Similar to the idea of a spar antenna, the radiation pattern of the original antenna can be reconfigured through proper reactive loading of the parasitic elements. The loading in the reconfigurable pixel antenna system, that is, the metallic pixels, are typically interconnected by electronically controllable switches, such as pin diodes or RF microelectro-mechanical systems, RF MEMS. By setting the on-off status of the switches in the parasitic layer, the radiation pattern of each antenna can be flexibly reconfigured. The more advanced reconfigurable antennas may integrate multiple reconfigurability in one single compact structure. The example in Figure 7 designed a compact pixel antenna with simultaneous pattern, frequency, and polarization reconfigurability. There are also relevant designs for reconfigurable antennas working at a high-frequency band, for example, millimeter wave. In our work, since we aim at improving the system throughput at the same time frequency spatial domain, we focus on the reconfigurable antenna with radiation pattern reconfigurability in the electromagnetic (EM) domain, which is seldom explored in the existing MIMO architectures. Before we move to the practical architecture of the proposed reconfigurable massive MIMO (RMMIMO) systems, we would like to provide a toy example to compare three types of MIMO systems, which aims to clarify the potential role RMMIMO could play during the evolution of MIMO systems. We consider the electric field intensity generated by a uniform linear array in the free space propagation. Three kinds of MIMO arrays with Hertz dipole antennas, HPAs, are compared. In traditional massive MIMO, TM-MIMO, the antenna element of the array is assumed to be a fixed Hertz dipole antenna, and the element number is assumed to be finite within a fixed antenna aperture. In reconfigurable massive MIMO, RMMIMO, the number of antennas is also assumed to be finite, but each Hertz dipole antenna is assumed to have a rotatable pattern. For holographic MIMO, we have both an infinite number of elements and a rotatable pattern for each antenna element. During the simulation, we keep the same array aperture for all different MIMO architectures. For TM-MIMO and RM-MIMO, with the increased number of antennas, we keep the array aperture and the size of each antenna fixed, but the antenna spacing is narrowed down. The mutual coupling and the reduction of antenna efficiency are not considered during the densification of antennas. Optimal singular value decomposition-based precoding is performed at the transmitter. As can be observed in Figure 9, RM-MIMO can provide extra performance gain over TM-MIMO in the EM radiation domain. And there is a performance gap between TM-MIMO and H-MIMO even for very large numbers of antennas. This is because the radiation pattern shape of a Hertz dipole antenna is not omnidirectional, but a sinusoidal function in the elevation direction. Observe that for large numbers of antennas, RM-MIMO can largely fill the performance gap between TM-MIMO and H-MIMO by adjusting the main lobe direction of each element's radiation pattern. For comparatively small numbers of antennas, which is of practical relevance, RM-MIMO can reduce the performance gap between TM-MIMO and H-MIMO. In fact, although the concept of full aperture surface manipulation of H-MIMO is tempting, it is practically difficult to realize for existing antenna fabrication ability. In this toy example, the mutual coupling effect and the reduction of antenna efficiency are not considered when the antenna number is very large. Actually, the performance of H-MIMO would be much worse when we consider more practical factors. Therefore, our article focuses on the region where the number of antennas is limited, which is of more practical relevance. Compared with H-MIMO, the RM-MIMO can only provide limited DOFS to manipulate the EM properties of the aperture surface. however, is a feasible solution to bridge the gap between the communication and EM theory, which might help to improve the performance of existing communication systems. We now consider a subconnected array-based MIMO system. The reconfigurable pixel antenna array is adopted to provide extra pattern reconfigurability. We consider the downlink transmission from the base station to multiple single antenna user equipment in the same cell. The downlink transmission model is given by equation 1 and the overall spectral efficiency is given by equation 2. Here, MIO is an n-dimensional vector used to index the adopted radiation pattern for each transmit antenna, which indicates the choice of radiation pattern combinations at the base station. Besides, the FRF is the analog precoder decided by the connection of phase shift network. FBB is the digital precoder and NU is the noise at the UE. To elaborate more on the radiation patterns, we exhibit an example of a detailed reconfigurable pixel antenna and its generated radiation patterns. As shown in Figure 11a, the design of the parasitic layer is the key to the reconfigurability of the radiation pattern, and the available patterns of each RPA are also constrained by the designed parasitic layer. In the example shown in Figure 11a, there are 12-pin switches for the parasitic layer above each antenna, which can potentially produce 4096 EMR patterns. However, not all the patterns are suitable for information transfer. Some offline genetic algorithms can be utilized to customize suitable pin connections, so that the desired steering angles can be customized. This helps to remove the unsuitable patterns to only keep the desired patterns that can be used. We consider a reconfigurable pattern set S with 4 types of patterns, as listed in Type 0 to Type 3 in Figure 11b, and the 2D horizontal and vertical cuts of them are depicted in Figure 11c. Intuitively, the EM radiation pattern of a TM MIMO antenna has a fixed mode like Type 0, which yields a lower coverage gain compared to RM MIMO with multiple pattern choices. In general, the extraparasitic layer does not incur much hardware cost and power consumption, since metallic pixels and electronically controllable switches are low cost and consume low energy. Thus, due to the reconfigurability of its patterns, the considered SCA-based RM MIMO is expected to achieve comparable performance as FCA and FDA-based TM MIMO but at a much lower hardware cost. Specifically, the NT element of channel HMIO in the time delay domain is given by 3GPP-TR38.901, as shown in equation 3. Different from the traditional massive MIMO system, the transmit radiation pattern of NT antenna is indexed by MIO-NT, which means the NT antenna chose the MUTH pattern in the set. The overall spectral efficiency optimization is then given as equation 4. To optimize SE, the joint design of the digital precoder FBB, analog precoder FRF, and EM radiation precoder MIO are needed. However, an efficient solution to this joint design problem is not yet available in the literature. The additional discrete-valued EMR precoder complicates the problem, rendering the joint design a highly complex mixed continuous discrete optimization problem. First, the search space of the EMR precoder expands exponentially with the number of transmit antennas, and it is impossible to traverse all options due to the prohibitive complexity. Second, for each EMR precoder in the search space, the SE is a highly non-convex and non-differentiable function, and it is very difficult to find an approximate objective function to optimize at a reasonable computational cost while ensuring good performance. Existing literature cannot solve the above problem efficiently, since they are proposed for small-scale MIMO systems or based on a pre-assumed pre-coding scheme for the fully digital array. They cannot scale up to massive MIMO systems with hybrid arrays and multi-user scenarios. To support multi-user and general wideband hybrid pre-coding in RM MIMO systems, we proposed a 3-level SE pre-coding algorithm, which split the optimization into 3 parts. Furthermore, according to the type of variables, the whole algorithm can be divided into 2 stages. In the first stage, an EMR domain pre-coding algorithm is employed to optimize the EMR precoder MIO. Given the optimal EMR precoder obtained in the first stage, we jointly optimize the analog and digital precoders based on the resulting equivalent channel, as traditional hybrid precoding algorithms do. Algorithm 1 provides a simple but effective greedy search algorithm for the first stage. The main idea of this greedy search scheme is to serially search the optimal pattern for one antenna while keeping the patterns of other antennas fixed. The search starts by initializing the pattern index of all transmit antennas to the traditional pattern. Then, during the search of each antenna, a standard hybrid precoding algorithm is applied for all possible radiation patterns in the set, and the pattern yielding the highest SE is selected for the current antenna. After all antennas have been configured one by one, the algorithm enters the next iteration until convergence. Observe that with this EMR domain precoding algorithm, the number of searches for the EMR precoder scales linearly with the number of antennas and the pattern set rather than the original exponential relationship. Therefore, a substantial amount of computational resources and time can be saved. Next, we evaluate the performance of the proposed SCA-based MIMO architecture. The channel model is generated by Quadriga software package. The simulation parameters are listed in Table 2, and we assume each antenna can choose one pattern from the total 4 choices from set S. In Figure 12, we assume one UE is served by base station, and we divide the geographic region into different parts according to the horizontal distance between the UE and the base station. As can be seen, the proposed MIMO architecture achieves a higher SE than MIMO for the UE at any distance. Intuitively, this can be explained by the fact that the EMR pattern used in this example is reconfigurable in the horizontal plane, and thus, a more flexible horizontal beam can be customized for a given channel environment. To verify the mechanism of how MIMO provides extra gain in a practical system, we plot the geographic distribution of SE gain achieved by MIMO. In Figure 13, the channel model is set to be line of sight dominated. It is clear that the UEs located at the edge of cells acquire relatively higher SE gain than other UEs. However, in the NLOS transmission case of Figure 14, the performance gains of the UEs have no obvious relationship with the UE's location. This is because the randomly distributed scatters complicate the channel environment. Nevertheless, the MIMO can still achieve performance gain. In Figure 15, we investigated the impact of the user pairing on the performance brought by MIMO. It reveals when one specific user is paired with different UEs, the relative performance gain is also different. Therefore, for multi-user transmission, user scheduling may also influence the gain provided by MIMO. In Figure 16, we compare the cumulative distribution functions, CDFs, of the SE for the considered different array architectures, that is, SCA-based MIMO, FDA-based MIMO, and SCA-based MIMO. When the number of scheduled UEs is 1, 2, 4, and 6, respectively, the average SE gain of SCA-based MIMO over SCA-based MIMO is 15.1%, 20%, 24.9%, and 33.3%, respectively. Intriguingly, in this application scenario, the proposed scheme even achieves a better SE than FDA-based MIMO. Besides, the relative SE gain provided by MIMO increases with the increased number of scheduled UEs, which indicates that the reconfigurability in the EMR domain can provide considerable SE gains. We also compare the energy efficiency of 3 considered array architectures, where we have considered the power consumed by the pin switches on the parasitic layer of MIMO. It can be seen from Figure 17 that the proposed SCA-based MIMO architecture offers significant energy efficiency benefits over FDA-based MIMO and SCA-based MIMO. As with any emerging technology, there are still many research challenges and open questions that need to be addressed to fully realize the potential of MIMO in wireless communications. Some key challenges may come from the following aspects. First, MIMO outperforms MIMO owing to the additional DU-FS in the EM radiation domain. However, there is no available research that analyzes the fundamental capacity limits of MIMO systems. Since the investigation of MIMO involves both signal processing and EMR pattern design, it calls for a fundamental analysis using tools from EM information theory for transmission modeling, DU-F analysis, and performance evaluation. Second, the reconfigurable pixel antenna discussed in this article only considers the reconfigurability of the radiation pattern shape in the E field. how to jointly excavate the EM properties of radiation pattern and polarization for multifunctional reconfigurable antenna is still a challenge. Third, in MIMO systems, CSI acquisition involves a completely new dimension owing to the reconfigurability of the EMR pattern. Therefore, channel estimation is a challenging task that must be resolved. It is impossible to estimate the full CSI at a time due to the fact that the training overhead increases linearly with the number of available EMR patterns. Therefore, how to design efficient channel estimation, CSI feedback, and channel tracking algorithms are also important. Fourth, the three-level pre-coding in MIMO systems is still a challenging task. It is critical to investigate low-complexity EMR domain pre-coding algorithms without sacrificing too much of the SE performance. Potential methods may include intelligent search algorithms, deep learning, and reinforcement learning. It is also important to consider the multi-cell inference and the statistical CSI when deploying MIMO in practical networks with the time-varying channel. Finally, due to the extra DoFS provided by MIMO, it is possible for us to integrate MIMO with other technologies, such as mode shift keying transmission, polarization modulation, integrated sensing and communications, and covert communication. In conclusion, an innovative MIMO system based on reconfigurable pixel antenna was proposed in this article. A typical example of multi-user downlink transmission was studied to demonstrate that SCA-based MIMO with three-level pre-coding is capable of achieving SEs and EEs that are noticeably superior to those of existing SCA and FDA-based TM-MIMO. Besides, we have also discussed critical challenges pertaining to MIMO and presented new research directions towards making MIMO a practical technology for 6G communication systems. Here are some main references for the slides. To find more information about this work, please refer to the original article below the video. Thanks for your attention.